All right. Got the mic up. Got people here. Hello, everybody. Let's transition over. So, hey to people who are here in the chat. Today we're doing a Learn With Me, which is a more casual session, not quite as sort of super focused as one of the classes itself. The goal is that we do learn some really cool stuff, but the difference is that we're going to learn together because I'm going to open up some code that I haven't opened up, and I'm not sure how it works, and I don't really know how everything works, and so I'm going to figure things out as I go, and I'm going to talk through concepts as I understand them and as I learn about them. Um, and I invite anybody who wants to talk through with me. So feel free to comment in the chat log. I have the combined YouTube and Twitch chat stream up on my screen, so y'all should be able to see each other's comments regardless of which stream you're viewing. And today we get to look at some really, really cool code. If you're not familiar with the creator, Timo Hoogland, he does beautiful work in Max 8. A lot of it focused around making really cool visuals and really cool audio as well. I don't want to leave out the really cool audio part of what he does, but I think his visuals in particular are a cut above the rest. And if you wanted to find his stuff, he has his own Gumroad where he sells his stuff, and he has his own Patreon where he sells his stuff. The code we're going to be looking at today, you don't need to buy. It's just available on his GitHub. And I have a link. You can see the link at the top of the stream to github.com/tmhglnd/Codevember 2019, which is what you see up here. If you want to see more of his stuff, you can just do a quick search for him. He comes up pretty quickly. So you can see on his site the sort of stuff that we can expect to get into today. Right? He's got beautiful visuals on display at pretty much every step of his process. And so that's a little bit more about him. Again, the code base that we're going to get into is here on GitHub. Again, that link will stay up on the top right corner of the stream. So to follow along with me today, all you need to do is go to his GitHub and grab this collection of patches that he's titled Codevember 2019. So last November, he set a challenge for himself to create a bunch of patches, one for each day of the month. And it looks like he got through 20. So maybe not quite one for each day, but one for most days of the month. And each patch is its own sort of self-contained, brilliant little thing. So I thought that we would start with the first one, the contrast one, and just see how far we get. Again, since I'm going to be learning a lot of the stuff as I go today, if I'm missing anything, if I'm getting caught up on anything, and anyone in the chat log has like, here's what I'm missing, here's the solution, or here's the answer to what I haven't quite figured out, feel free to contribute. I'd love to hear from people, no matter where you're watching from or what level of Max Coder you're at. So let me show you how to grab these files. If you're on the GitHub page and you don't have history using GitHub, the easiest way to grab these is to go to the green button where it says clone or download, and you can click on that green button. And the clone is really useful if you're familiar with Git and Git commands, but all you really need to do is hit download zip, which will download everything in this collection of files as a single zipped folder. So you'll hit download zip, and in your downloads folder then you will find the zipped file, which I have already downloaded, but you can see it's still compressed. So it should say Codevember 2019 master.zip. We do want to uncompress this folder. We don't want to just navigate in and then find something from there, because we'll need all of the files uncompressed to make sure that patchers see each other when he's working with externals or abstractions. So I'm going to extract all. I'll just put it in the same folder. And then, so it made its own master folder. See, there's another master within there, so a bit of redundancy. But if we open that, we can see we've got media, patchers, and the license and README are sort of Git, not requirements, but Git standards. So I don't think there's anything too important. The README file is this. So he's just giving us a list of the names of the patches and how to do what we just did. So it does say that there are some dependencies. The GL3 engine, ease, siphon, and jit.mo. Siphon's a tricky one because that's Mac only and I'm working with Windows. But what we'll do is we will deal with these dependencies as we get to them. Siphon, there's a Windows equivalent called Spout, so maybe I'll just swap out some code as needed, but we may not even need to do that. So either way, we'll leave the copyright as it is. And let's just get into it. So we have media, which I suspect, ooh, pretty. So these look like movies. Maybe they're movies that we're going to call up in the patches themselves. So we can see that we actually have a movie. It looks like a movie for each patch. So either it's a movie that we're going to use in the patch, or maybe it's just a quick bounce down of what he's made. But the main attraction here is the patchers folder. And it looks like he starts with a template and then gets into it from there. And so we've got some duplicates. My guess is that some of these duplicates are actually going to be called up. Not duplicates, I shouldn't say that. We have some that have duplicate numbers on them. And my guess is that some of these will be used as abstractions within the top level one. But let's crack open the template. And I've looked at some of Timo Hoogland's code in the past, and so I kind of know that he has a template that he likes to work off of. And my guess with that is that this is his template. So we're probably going to see code that looks a lot like this in all the patches that we work with today. So if we did a really quick check over what's in the template, I can see that we have a preset object here, which is probably being used just to create different presets to show off the code once it's done. And we're loading the preset. We're doing a defer low on the load, make sure everything else that needs to load loads first. Then we can turn on, so when I hit this toggle, we're going to turn on the rendering of the video in the jit.world, and we're going to turn on the DAC. So there is some stuff going to the MC DAC, so things might get loud. I don't know. Let's just find out. Okay. So there's nothing going on by default over here, which makes sense. But if we basically want to see what's happening, the jit.world is rendering a three-dimensional scene on the GPU. That's pretty much the function of the jit.world object. And he's set it to have anti-aliasing on. The erase color is just going to ensure that when it renders a new frame, that it sort of clears the previous frame. I think that's what erase color does. Size is setting the size of the rendering to 270 pixels by 270 pixels, so pretty small rendering, which is good for GPU load. The dimensions, the internal dimensions will be 720 by 720. And then this is floating, which means that it will always stay on top, even if we click on other windows. Let's see. Then we have connected to that jit.gl.node. And I'm trying to remember, as best I understand, and if anyone knows better, you can tell me. I think what the jit.gl node does is it takes the context of the jit.world and sort of slices off a separate instance or a separate space within that context to render stuff individually, so you can sort of have multiple things rendering within the same quote-unquote context. and that's going into a sub patch that he calls tilt blur. And I don't know what's in the sub patch. A lot of jit.gl slab stuff and jit.gl pick stuff. So this gets pretty deep actually. But since this is all, ooh, yeah, look at that. So we got some Gaussian blur going on here. Um, and we're running through, I guess, 4 instances of the Gaussian blur. I'm guessing this is just a way to make sure that the rendering setup is working and that we can actually see something changing to whatever it is you're going to put into the jit.world. So remember that this is a template, and he's going to be building off this template. And then over here we have MC Mixdown. I'm guessing he's planning to, populate whatever audio processing he wants above the mixdown, and then he'll mix it down into one or how many channels? Yeah, 1 or 2 channels. Add some panning. I think the Yoffer 2 is an old sample patch from the examples that oh no, it's reverb. Yeah. So this is a classic reverb algorithm. And so he's mixing down whatever we're going to build, add some reverb to it, add a 1-pole filter to it. OMX is compression. This is just a sort of pre-built compression algorithm. Then we're going to send that out. And then snapshot, what that's going to do is that's going to allow Timo, or allow us, to convert the audio signal into a stream of max data. And once it's max data, you can use it to manipulate whatever you want. So that's his template. But let's see the template in action. So I'm going to close that, and let's open up the first patch, which is contrast. Yeah, and unsurprisingly, we're seeing a lot of the same code. Not all of it, but a lot of the same code. And what we're getting is this cool render. Very cool. So it's called contrast. So you can kind of see why, right? We've got a black, half white background, and it's rotating. It's positioning, and then it looks like it's sort of supposed to appear, It looks like it's supposed to appear as if when the object passes from the white to the black, that you see the wireframe. And it kind of looks like that, except for the wireframe isn't exactly right because we're working with a square on the white background, or a cube on the white background, and a sort of pyramid shape on the black background. And maybe there's an easy way to fix that once we know how this is working. Or maybe that's intentional. But either way, let's pop that up into one corner so we can see that as we work. And then I will just make sure that we're not overlapping on what we're seeing in here. So it looks like we are also rendering audio, but I'm not hearing the audio. And it's not being sent out to y'all either. So let me check my audio status really quickly. So it says it's going to the correct device. Interesting. Maybe we're not really intended to hear that. Well, we're getting audio output there. I've got my device set up properly. It would be good to know. No, it says zoom output capture. We're not capturing anything. So maybe if I turn on the DAC, turn on and off the DAC. Okay. We got noise being mixed down. Maybe the truth is that what we're getting is not within the audible range. So maybe there's a reason behind that we just haven't figured out yet. As if I pull up the audio tester, we should be able to hear some audio if I generate a sine wave. Uh-oh. We're not hearing that either, so it looks like there is something wrong with my setup. Let me check. Okay, that we definitely heard. That's a pain. I wonder if I go to the audio status and try nudging this a little bit. I'll just swap to something else and then swap back. I'm not going to stick with this for too long because the real appeal here is I want to see how this rotation's happening. So if this continues to not work, I will just give up on audio. Whoa. Okay. Okay. Glad I didn't give up on audio. We've got that working. But that's pretty wild. So I'm going to turn that down. And that's probably the easier thing to figure out is the audio and how that's working. So it looks like we have. I'm not really seeing these two things connect, but I could just be missing something. It looks like we have some noise at the MC.noise that's being filtered in this FFT from MTX subpatch. So there's that. We have a fast Fourier transform, which we'll come back to in a bit, but it looks like we're filtering noise and panning it to get that fun output there. And then it looks like all the animation setup is occurring here. So I can see JIT.GL Plato is making shapes right there and animating those shapes. So we'll come back to this in more detail, but yeah, we have the tetras, which is the tetrahedrons, those, and our cubes, those. So we're creating our shapes here. And then it looks like we're doing some more things with textures here that may have to do with how we're creating the background. And we have a couple of camera position setups here. Okay, so let's try and break this down, starting with the creation of the shapes. We have just a couple of things that we can interact with. Not too many points. We have the ability to turn on and off the processing of JIT.world. Then we have it looks like turning our shapes occurs from this input here. And then speed and rotation for some other things happening here. So we can see rotation and speed. And rotation's being updated automatically. So there must be something going on in this jit.mode.time object. And if I crack this open, jit.mode.time outputs float time values using specified mode for real-time animation. Okay, so we'll come back to that. Let's try changing some of these values to see what happens. So we've got this main value at 5. Let's set it to 1. Okay, and no surprise, that slowed down the speed at which this is turning. And if I set that to 10, now it's going really fast. 100, super fast. Cool. So I'm not sure what the -4 speed is affecting. Let's try changing. So it's -0.4. Let's set it to -2. So a larger negative value. Oh, look at that. That's increasing the rotation of this background color swap. So that's really neat. And if I change it to a positive value, it starts moving in the other direction. Also really neat. And I can set that to a really high value. Nice, really cool. Slow that down. All right, okay, cool. So we know what each thing is controlling. I'll set that back to its default. And so the rotation of the shapes is actually separate from the rotation of the plane itself. Cool. All right. So we start with the creation of the shapes. We have 4 shapes, 2 cubes, and two tetrahedrons. If we open up the help file for jit.gl.plato, we can see that that's what it does. It creates shapes. We can choose different shapes from these options. Cool. So the jit.gl Plato creates shapes, and it sends it to a render context, right? So the way that jit.world works, so jit.world can have a name that's specified for its context, but it's not required. Okay, I do remember this part. And remember how I said that the jit.gl node creates sort of separate spaces in a jit.world context. So jit.world deals with the process of rendering a three-dimensional space and outputting that render to a window. So it does all of that in one. And then within that three-dimensional space, you can have one or more sort of planes, or one or more nodes, as they call it. And you can think of these as like almost like parallel dimensions within the same context. And I think that that's sort of what's going on here. So we have two nodes, jit.gl node, and these are both named. We have @name to give this a distinct name, and one is called tetras for the tetrahedrons, and one is called cubes for the cubes. And if you look, let's see. So I believe that if they're not pointing to a specific jit.world, then they will point to the local. So in other words, if the jit.world is not named, they will render to the closest jit.world, which just happens to be this one here. And we can double check that. So yeah, jit.gl node create hierarchical rendering group. Use jit.gl node to construct hierarchical rendering groups. Nodes create subcontexts of child objects that can be modified, rendered, and captured together as a functional group. Right. And in all of these examples, there is a jit.world, right? Because that's what's required to render to. And the subcontext is key. So the nodes are subcontext to the jit.world context. So we have basically two separate worlds that are existing here. One called tetras for our tetrahedrons, and one called cubes for our cubes. So they're separate, and then there's some secret sauce that's going on in the jit.gl.pix that is combining them onto one plane and then affecting how much is being displayed on each plane at any given time and where on the plane it's being displayed. And so if we look at some things that are connected to this, right, we have our jit.gl camera, objects to draw to this jit.gl node. So here's the weird thing about jit.gl node. You tell the node what you want to draw, right? And you can do that by sending, by rendering elements to that context using the name, right? So we're rendering context to that element using their name. Cubes goes to cubes, and Plato goes to Plato. But then we can also connect objects to it to tell it to render those using the second outlet. And it's very, very strange to me that that a max object wants to connect to something else in order to say what's going on within that object. It almost feels like it's reverse of the traditional max flow, where you send something to something by plugging into an inlet. And yet that seems to be how jit.gl node works. So let's see what the camera does. Jit.gl camera sets a rendering view. So let's read the description. Sets the properties needed to define a view in OpenGL. Right, so you render things on the graphics card, but then we have to have if we wanted to see that, right, we would need to define the viewport, kind of define what it is that we are seeing exactly. So that's what the jit.gl camera defines. Says these include field of view, clipping planes, perspective or orthographic projection modes. In addition, a position and orientation can be defined for a virtual camera. And you can see there's like all of these different attributes for it. And what I've noticed with a lot of JIT objects is that um, a lot of values are set via attributes as opposed to the traditional max and MSP method of just sending specially defined, specially prepared messages, right? So whereas with a max object, you may say lens angle space 45. In a JIT object, it's going to be an attribute at lens angle space 45. And because of that, I see lots of attrui objects throughout JIT help files. It seems to be the preferred method of working. So that's kind of strange, but it does mean that we can use that knowledge to our advantage as we figure stuff out. How are y'all doing, by the way? I see people in the chat log, but no one's chimed in to say hello. Hope you're all doing well and finding this to be interesting to sort of hack through. So we're defining by connecting the camera to JIT.node. Again, it's sort of in reverse of what we're used to thinking, but we're connecting the camera to the node. We're defining our view into the node. So we're setting an X, Y, and Z position, lens angle, and I don't know what near clip does, but we could go back if we really wanted to figure that out. Could go back to the reference. Yeah, you see how many attributes there are. Near clipping plane distance. Okay, that's still a bit vague to me. Hey, thanks for saying hi. Real Illusions, thanks for joining us. So YouTube wins today. YouTube made the first comment before Twitch. Cool. That's the opposite of the last stream. So yeah, I'm not super clear with what near clip means. Maybe if you're more familiar with jitter, you can help us out. But we're basically just establishing the parameters for the camera. But it looks like we're not rotating the camera. We're doing a rotation in the jit.gl.pix file, and this is where it's going to get a little hairier. So we have our two contexts, and we're probably. Oh, hi, Darren. Yeah, you're one of my patrons, aren't you? So I'm glad you could join in real time on YouTube. Okay, so here's what's happening inside of this jit.gl.pix, and before we dive into that, I do want to go to the help file really quickly. What jit.glpix is it's basically another form of subpatcher. So, we've got subpatchers, abstractions, polytilde. Jit.gl.pix is another patch within a patch. But it's a patch within a patch that is designed to allow us to do pixel shader processing. So we're going to render some sort of effect onto a context. Right? So we're doing something to a context within jit.gl.pix, and what that something is up to your imagination and your comfort in the gl.pix objects. So that's why I can double click on it and it gets a new screen. I believe you can save patches and load them into jit.gl.pix, just like you can with abstractions and with polytilde. But you don't have to. And so that's what he's doing here. He's just sort of treating this like a sub patch. And we have ins and outs. So that's like polytilde, right? In one, in two, out one. and and we have objects that are sort of unique to jit.glpix here. Um, so let's see. We have a switch. So we're sending in our tetras in here and our cubes in here. That's N1 and N2. And I'm not sure what the minus operand arithmetic does um, in the jit.glpix. That's different from a normal one. So it says reverse subtraction. Subtract first input from second input. So we're taking the entire context and inverting it effectively, because 1 minus um, the initial value under. Can we view this? So if I can I make a print object? No, you can't make a print object in jit.glpix. Yeah, so it's mysterious. But we have a switch, and notice that the help in jit.glpix are not full help files, but just these little pop-ups that appear in the patch. And then you can go to the reference from there. So this is actually pretty useful. This is the gen common operators reference. Um, so the way that gen works, since we're talking about gen now too, right? We just really blasted wide the scope of what Max can do. Um, Gen processes everything simultaneously for every pass for what's happening inside of it. So um, since this is happening in JIT, it's a JIT gen collection. All of this stuff occurs, all the processes in here occur every frame that gets rendered, all at the same time. So, and it will do that every frame. So let's see if I can find the subtract operator in here. Returns 1 if it's not equal 1. Constant, declare, expression, ignore, pass. In defines input for gen patch, out defines output. Bang or not, an input value of 0 returns 1. Any other value returns 0. Okay, so it's returning, here's bang minus, reverse subtraction, which is what it said before, but that's not super helpful. So it's just going to 1 minus whatever it receives, and I'm guessing that that is the content of the frame in this case. Okay, we got to keep going because I'm not totally clear still, but so switch says selects between the second and third inputs according to the Boolean value of the first. If the first argument is true, the second argument will be output. Otherwise, the third argument will be output. Okay, so it's going to toggle between the tetrahedron render and the cube render. We really should get Timo on this chat so he can tell us exactly what he's doing. So then before we go any further, we have everything that's happening here. S norm, swizz, car2 pole. There's our rotate param. Wrap and then less than pi. Okay, we're getting into some heavy stuff here. Signal normalize coordinates of input matrix. So the input matrix should be what's coming in the left inlet, although I don't know, we've got two input matrices, right? So we're getting the signal normalized coordinates of the input matrices, and normalized to me means that we're stripping off the negative, right? Or maybe we're just wrapping it within the range of -1 to +1. And then swizz, unpack and remap. So we're unpacking the x value of the matrix and the y value of the matrix. So this is very similar to an unpack in the normal world, but we're separating x and y so that we can send the x and y values to car to pole, which is a converting the Cartesian values to polar format. Angles are in radians. Oh boy, okay, okay. Tricky. So we're getting out of the left outlet distance value and out of the right one angle. Now angle is interesting because we can see that we're dealing with angle here. Um, and we're getting a slowly rotating value. So I'm really struggling to wrap my head around every single part of this, but what I can tell is that um, we have a we have a switch, right? And we're determining which part of the screen we're seeing, and then we have angle from our polar coordinates coming out here as radians, and we're changing that angle value based on the rotation that we've set over here. So we're just getting a slowly changing angle, which we're adding to the default angle of the view. And so here we're getting the what I'm guessing is that depending on the angle that we have set here from the rotation, we're switching whether we're showing the tetrahedrons or the cubes. And then we're wrapping. So I'm guessing what this is doing is making sure that everything stays within the appropriate range as we do that rotation. So wrap 0 to pi. Low and high values can be specified. So a wrap simply says whenever anything goes outside of the expected range, wrap it back into the expected range. And the trick here is it's hard to see exactly what's going on at each point without having some view into the patch. We can't use print, but I wonder if there's like a gin.print. Hey, Timo's here. This is the person who actually put this patch together. Thank you so much for joining. Okay, so the bang minus 1 inverts the color. We have like all the answers are right here on the screen. Bang minus 1 inverts the color. Okay, so 1 minus black is white, 1 minus white is black. Okay, cool. Um, so that's how we're getting we've got cubes plugged in there. And let's see, you can connect out 1 to different objects in the GL pix and see what the output is. Connect output 1 to different objects in the GL pix and see what the output is. I'm not sure I follow you, Timo, at that last part. Like, so what should I connect to that? Like I could swap them, right? I could take the output of this and plug it in, which is cool. I like this because now we're just inverting the colors based on where we are, right? And I could probably swap these as well. Oh no, we have to have something going into the leftmost inlet to generate the output result, don't we? That's good to know. But we could reroute so that the same item is going out of both. So that part makes sense. So what we're saying then is that what we're getting, if the minus 1 happens on N2, or the bang minus 1 inverts the color, we're generating an image with a black background and a white object, and then the bang minus 1, 1 minus white is black. No, we're generating a white background with a black object. And so we're basically just inverting the color with that switch. I'm still not totally clear as to how we're combining the two nodes in here, because the switch says it toggles between the second and third inlet. Out 1 is connected to the switch, but if you connect it to just in 1, you see only that. helpful as a print. Out 1 is connected to switch, right? Oh, but if you connect it just to in 1, okay. Right. So that's what you're actually making a black background with white items. Yeah, so there's in 2. But it's only rendering in 1 in this case, even if we connect it to in 2. And that's what the S norm is putting out. So this is actually really smart. Thank you, Timo, for that hint. So we can visualize what we would get out of each of these elements. Although it doesn't seem to work there. That's interesting. Ah, and that's how we get the ultimate output. Okay, so we can see if we connect in 1 to out 1, we get our tetras. And I'm guessing because I disconnected that, if I put our cubes back in. Yeah, so that's what we're rendering on the cubes. That's what we're rendering on the tetras. This is the inverted version of whatever we render, right? Now the S norm is still kind of getting me. I'm not sure I totally understand that. So let's see. Signal normalized coordinates of input matrix. But what is the input matrix? In this case, it's the tetras. Yeah, I can get rid of that gen print. So why do we see this output? Maybe, I guess there isn't any better help for S norm than that. Why does this input matrix become signal normalized to this? Or is S norm its own thing? Either way, I can see that we have X and Y coordinates. There's the cartopole output, which is our angular conversion. I can still see that, there's the output of what we're getting, that rotating color field, or not color field, but black and white background. And so why does that have an effect in the switch? Condition to test. Oh, I see. S norm gives signed coordinates. Left determines input matrix. So that's what I thought. So it's showing us, it's doing something to the tetras. Basically, it's -1 to 1 XY coordinates for every pixel. -1 to 1 XY coordinate for every pixel. The Cartesian coordinate system. Okay. Sign norm, that's what makes it 1. Go 1 to 1. Hey Alex, thanks for joining us and thanks for following too. So maybe someone can explain to me what a signed norm is. I don't actually think I follow that. Left in that determines input matrix. I got that part. So it's giving us the signed norm for the input matrix. -1 to 1 XY. I don't know what stream elements is, Alex. I mean I'm pretty new to Streamlabs, so yeah, sorry, I'm just not sure. So I'd still love. It sounds like Real Illusion. You've got a pretty good grasp on this, and Timo, if you're still there, I'd love to get either one of your help as to what it means to have the sign norm. Sign normalized coordinates. Because what I want to understand is why we're getting. Oops, I just disconnected that. Why we're getting this black to white output here, going from left to right, and then black to white going from top to bottom. I do think I'm starting to understand that as we get the rotating black half and white half, that that's the test for um, which output we get, right? Because as we're getting a um, a black background, right? We're switching to that image, right? And if we have a white background, we're switching to the white image. Although it looks like it might actually be, yeah, more or less. Or maybe it reverses that. It looks like. Um, so the switch also doesn't do exactly what I thought. Selects between the second and third inputs according to the Boolean value of the first. Um, oh, oh, interesting. Wait. So the Boolean value, this whole black range would be a Boolean value of 0. And this range, the white range, would be a Boolean value of 1, right? So it's filling in the zeroth um, node in the black space, right? That's what Switch is doing. That's what I'm guessing Switch is doing. It's saying fill in the zeroth render here and the first render here. Every pixel has an XY coordinate value, which you can get with the cell. If you divide those coordinates by the total dimension, you get normalized. Okay, every pixel has an XY coordinate value. That makes sense. If you divide those coordinates by the total dimension, width and height, you get normalized. Okay. Um, that one's still kind of. I mean, there are some concepts that are pretty tricky to grok here, but I love that I get the chance to grapple with it. Um, because they're trying to figure out like what I want to understand is why that creates a static image, right? Because if every pixel, okay, so we're worried about we're considering the coordinate values of each pixel, which would be just each pixel in the frame, and that means that the coordinate values are static because the pixels don't move, right? The pixels are static. So if you take each pixel and divide each pixel by the dimension, the total dimension, width by height, then we would get a static image. Normalized, if you multiply those by 2 and subtract by 1. Huh. You get normalized. It's just scaling your range 0 to 1. Yeah, okay. And so as we move from left to right in that scenario, okay. So in other words, um, it's stating for each pixel along the x-axis in this case of the image, we're going to have a value between 0 and 1 that increases from left to right as we go across. So we're just getting an output of values that starts at 0 on the left side and ends at 1 on the right side. And then we get the same thing from y, a range of values that starts at 0 and ends at 1 as we move across the matrix. And that's what that looks like normalized when we combine the x and y together. Because we're really talking about alpha, red, green, and blue. I think that's what I'm understanding. At least I'm getting a lot closer. So then we convert that from Cartesian coordinates to polar coordinates. It only starts at -1. Okay, thank you. So we're going from, instead of not 0 to 1, but -1 to +1. Whew, that took me a minute. But Timo, thank you so much. And Real Illusions, thank you both so much for helping me connect those two things together. Um, it's it took me a while to figure out why that was static, but it's because it's not actually concerned with what's in the pixels. It's just concerned that we have pixels at each of these locations. Okay, cool. So with the polar coordinates, we have this um, information translated to radians. Um, and I don't know why we get just a black output from the plus, but once we wrap it, um, so so there's still some really tricky stuff going on here, right? Because when we convert it to radians, it changes the view of that, but we need it to be in radians so that we can rotate it appropriately. Um, Once we do that, we wrap that range from instead of from -1 to +1 to 0 to 2 pi. And then if it's less than pi, which half of it will be, we get a 0, a Boolean of 0. And if it's greater than pi, because we've gone from -1, +1 is now 0 to 2 pi, we get the output of 1. Or if that's not exactly it, we're now really close. But either way, what we're getting is a matrix where every value is either 0 or -1. That's not totally. Yeah, every value is 0 or every value is 1. And then we take that matrix and use that as our switch between the first and the second input. So for every grid point on this matrix that's a 0, the switch will output our tetras. And for every element of the matrix that's 1, the switch will output. Oh, no, no, no. It's the opposite, because this is value of true, and this is value of false. So, yeah. So that value is per pixel, not just everything all at once. It's per pixel. And since we have however many pixels are being rendered, 720 by 720, it determines that on a pixel by pixel basis. Okay. Whew. I think that makes sense to me. And thank you, Timo and Real Illusions, for helping fill in the blanks there. There's still just like a couple of very minor blanks around what exactly is happening after the Cartopole. So if it's coming out as Cartesian coordinates, are those values, what values are we getting there? Is it -1 to +1, or is it 0 to 360? That would be 0 to 360, right? Or is it 0 to pi? So there's still a couple of questions there, but they'd probably be pretty easy to clarify once we got feedback or once we looked it up. But either way, what we're ending up with is 0 to 2 pi, and then on a per pixel basis. And that's rotating based on this addition parameter. Okay. So that's all what's happening in the jit.gl pic. So we make our shapes and render them to the individual nodes. Those are separate contexts that are being rendered by jit.world. Then in the jit.gl pics, we determine which of those two renders will actually be rendered by the video plane, depending on the rotation. So the video plane is the final bit here. -pi to pi, okay. -pi to pi is the range. After the plus is black because the rotation is already at -500. Okay. So just to come back to here, he's saying what's coming out of here is -pi, 2 pi, and then we add our rotation to that, which is going to be a very, very large negative number. And so the only thing that it can output is black. Then we wrap that to an appropriate range of values, 0 to 2 pi. Okay. So then finally that texture is being sent to the jit.gl video plane. And so if we look at what video plane does, displays video, and OpenGL provides a quick way to show video. And, oh, that must be for recording purposes. Is that what that is? Yeah, the actual purpose of the video plane here is not totally clear to me. But we're connecting that output to the video plane with a value of transform reset 2. And we look at the reference for transform reset. Model view and projection transform reset flag, default 0. When the flag is set, the model view and projection transforms are set to the identity transform before rendering the object. This is useful for sprite or billboard overlays or automatic scaling to window size. 2 says a orthographic normalized GL ortho, -1 to 1, -1 to 1, near clip, far clip. Okay, that's another tricky one. Orthographic normalized GL ortho. So that's something that is a setting that OpenGL understands and expects to work with. But typically the GL video plane is set to render a video to the jit.world context. I don't know why we have to send that to the video plane to render it, to show it. But I suspect that if we don't hook that up, it will not show anymore. Oh, it does still show, but it warped it. Oh, it doesn't even warp it. Yeah, I'm assuming that's for a different purpose. Or if we delete that, then it doesn't show. So it is required to get that final bit of rendering done. Because it's a two-dimensional plane at this point, like jit.gl pix is outputting something as not two-dimensional, but as a flat plane instead of a 3D rendered plane, potentially. The siphon server allows us to view this output in a different program. So if I wanted to send it directly to Streamlabs, which I'm not doing here, I could use the siphon server, but that's not required for the rest of what's going on here. Okay, and then I think the noise, I don't see the music being directly related to this, so it might be something that is just some enjoyable, fun noise to listen to while we render this. All right. So we can see, just to sort of finish cleaning up, the nodes themselves, through the shapes themselves, it is related. Okay, so it's related, but we need to understand how it's related. mc.list, mc.noise. We have a PFFT. We're doing a Fourier transform to the sound. Mixing it down. mc.list 1 and 2. So I'm sort of looking around. I'm just trying to see where those elements connect. And we have the S render, but that's not being sent to anywhere. Maybe there's a hint in here. Jit.peak spec. Ah, I was just about, it was like right there. Yeah, the jit.peak at spec. So jit.matrix to jit.peak. So let's open matrix data as an audio signal, right? And as we can see, the JIT.peak wants the name of a matrix, so it's looking for a matrix called spec, right? So the next thing that we want to look for, there's JIT.matrix. Here's the spec. Okay, so this is what ties the video to the audio. All right, so we're taking the output of the jit.gl.pix and sending it to jit.gl texture. And what this is doing is it's taking the texture that's being output by the pix object and rendering the first 128 by 128 pixels of that. And I'm not sure what the async read is doing to help with this. Read back from an OpenGL frame buffer. Okay, so the async read reads the OpenGL texture. Performance gain. To perform asynchronous reads the OpenGL context at high frame rates. Read back from an OpenGL buffer. So it's reading so that's the OpenGL buffer, is that 128 by 128 texture, but I'm not sure why we need that asynchronous read there. Obviously, if I delete it, things stop working. And that's what we get if we bypass it. So what is it doing in the meantime? Is it compressing the entire image down? Is it because it looks like if we just took the tiniest bit of data from there, it does look like it's compressing down that entire image into a much, much smaller frame. But when we don't do that, when we bypass the async read, we can still get output. But it's clearly not the same. It's more efficient reading texture to matrix. Okay, so it's converting it back into the matrix. I think that's what might have been missing from my brain. Yeah, okay, I see. Because we're moving from the jit.gl domain, which is where we get OpenGL contexts. Yeah. So we can see that when we're working on the graphics card OpenGL, we have GL textures. And to get back to the matrix domain, we have to convert it from a texture to a matrix. And that's what the jit.gl.async read does, which allows us to send it into a pack. Yeah. So so if we remove the pack, it looks actually similar to if we went straight through. So pack 1, offset 1. Pack makes a multiplane matrix out of single plane matrices. And then what does the offset 1 do? Input plane offset into input matrix, default all zeros. So we're offsetting it onto plane 1. So we're starting on plane 1. We're taking everything RGBA and putting it into the first plane. But it doesn't matter because as long as it's one plane, we'll just translate all of that as black and white data. Matrix spec. I'm trying to figure out what spec does with jit.matrix, because if we don't have spec, what do we get? Or if we bypass the jit.matrix, what do we get? Oh, duh. Okay, so sorry. So then we're sending it to a named matrix. And by placing it into a named matrix, we can then grab it in the PFFT in the jit.peak. So jit.peak takes this matrix, right, which is our um, pretty low res, but our matricy version of the jit.gl texture, and converting that to an audio signal. So that's how they connect. That's pretty wild. For a patch that doesn't look this involved, there's actually a lot of stuff going on in very thoughtful ways. So the jit.peak reads the value of one plane of a matrix, um, one plane of a matrix cell at the position specified by the signal inputs. This value is output as a signal. So we specify with jit.peak the name of the matrix and then the cell, the x and y coordinates. No, x and y coordinates are expected as the two inputs, which we're getting from the FFT 1 into N. Ooh, okay. Scale 0 to 56, 0 to 56.7. So bin index. Jeez. There's a lot going on here. So we're affecting the noise. So we've got MC noise coming in here, and we are effectively changing the noise on a bin by bin basis, based on the one of the values in the video. And that the cell that we're selecting is also determined by the FFT. It's being determined by this list, mc.list 1 through 3. 1 and 3. So mc.list creates a multi-channel signal from a list of values. So the list in this case is 1 and 3. That's pretty easy. So in other words, I don't know why this, there we go, decided to start working kind of. Yeah. So it's just a way of generating constant streams of signals, right? If we send it 8 and 10, then it sends out a constant stream of 8 and 10. So the MC list over here is sending out a stream of 1 and 3, while the MC list over here is sending out a stream of 0 and 1. So that's being used for panning, but what I'm interested here is how we're filtering the noise in the FFT. So we take the amplitude, convert it to the FFT image. In the FFT image, what we get is real input, imaginary input, and bin index. So we're doing an analysis of energy per bin. We're converting that from Cartesian to polar coordinates. And we get from when we do that conversion, we get from the left output amplitude. The right output, we get phase. So we are adjusting the amplitude of noise in each of the bins. I'm trying to sort of shortcut it and figure out what I think is how this is working, and then I can see if I can prove it or disprove it. But we are adjusting the amplitude at each frequency bin of the noise. So we start out with noise, which is random energy across all bins at equal amplitude, and then filtering that the amount of energy across the entire frequency spectrum per bin based on the darkness of, or maybe the brightness, probably the brightness of the image at a corresponding cell. Now we're doing something interesting with the bin information. We're scaling it. So we have 257 bins for our analysis, and we're scaling it, or the bin index, from 0 to 256. So we're sort of rescaling it to the same range, except for we're doing an exponential. We're changing the curve of the scaling. So with the scale object, yeah, the scaling curve is the final argument. So with the scaling curve being less than 1 in the classic mode, the typical value of argument's 1.06, which gives you logarithmic. I'm not sure what so I guess if it's less than 1, we get, instead of a curve that goes like this, we get a curve that goes like this. So it's just the shape of the exponential curve. But I'm not sure how that benefits us with the peak. Because what we're doing is we're moving through the x and y coordinates depending on the bin, and that's allowing us to then choose the multiple for the signal per bin. And then we convert it back to Cartesian coordinates and output to an audio signal. So that might be the final question, is how exactly this list, because we're getting a 1 in channel 1 and a 3 in channel 2, what that real value does, so the 1 and the 3, what that does, so we're choosing, because I mean in my brain what that says is sort of, we're choosing x to equal 1 or x to equal 3. That doesn't seem that impactful, so I feel like I'm missing something kind of important there. And then what we're doing here is we're choosing the y coordinate, and we're sort of just like scrubbing down through the y coordinates as we move through the various frequency bins. So at the very least, assuming that I have this right and I'm not missing anything else, we're choosing a different x coordinate for the left channel of noise and the right channel of noise. And then per bin, we're choosing a different y coordinate so that each part of the frequency spectrum has its own sort of unique cell in the final image. And we will look at that cell and grab its value to determine the multiple for the amplitude at that point. So we're actually scaling the amplitude per frequency bin based on the darkness or the brightness of a cell in the graph, which sounds like this. Oh, I gotta turn the volume back on. Whoa. Okay, so 1 and 3 choose the slices from the matrix. One left channel, other one right channel. The scaling gives more precision in the low end. Oh, interesting. More precision in the low end. Huh. Okay. So the other bits of code in here, we've figured out how we're filtering noise based on the coordinates in the graph. We know that we are placing objects into subcontexts via the jit.gl Plato going to our jit.gl node objects. And we are rotating those, which is something that we haven't looked at yet, but we're rotating the objects using the jit.anim node objects, which we have actually several of them linked together. And this part is probably less complicated, but we do have this notion that we start with the jit.anim drive, and we're giving it a value of turn 0.2, 1 currently, 0.2. The jit.anim drive says animate a 3D transform. Animates relative transforms over time with easing. The jit.anim drive object works in conjunction with jit.anim node, which is what it's hooked up to. In OpenGL objects to perform this function, double-clicking the object will open a UI mapping directory, allowing certain user interface actions to be mapped to animation messages. So the animation message is turn, and we're animating the node, the jit.gl node. Here's our animation directory. Look at that. Key map ADZQWS, mouse map, mouse down, and mouse vertical. So those are mappings for the keyboard. It's kind of interesting. But what's kind of critical here is that we're sending a turn message to the drive, and that outputs. Here's what that's outputting. Anim turn 0.2, 1, 0.2, and then rotating number, which is going to jit.anim node. And the thing that's kind of weirdest to me is how these are chained together. So jit.anim node performs hierarchical transformations. The jit.anim node object represents a transformation, position, orientation, and scale in 3D space. It represents a transformation in 3D space. OpenGL objects bind to a jit.anim node and receive position, rotation, and scale attributes. So these are binding by sort of trickling down. Is that what's happening? So we have a master jit.anim node, which is being bound to these two sub nodes, which then go into more subnodes so that they can be bound to the individual cubes. And we're saying what do we want to have this be bound to is position. Jit.anim node. And I bet we can animate a lot of different things. Doesn't have to be position. Yeah, we have rotate, scale, position, specifies a position in 3D space. The position is relative to the position provided by the parent node, default 0, 0, 0. Okay, so we are turning, using jit.drive, we're setting this animate turn. And what are we turning? We are turning the position. On what? On our nodes. Sorry, not on our nodes, on our shapes that are being rendered in 3D space in the nodes. Whew. So as you can tell from if you've hung out and watched me along with this, I have a lot to learn about jitter and even more to learn about jit.gl. But this is starting to clarify certain things in my mind. And I can't wait to dig into more of Timo's patches, because I think this will continue to clarify things for me, and hopefully this did help to some degree to clarify things for anyone who was watching who hadn't been introduced to these concepts before. But I think I am going to wrap it up here today. So thank you, Timo, for actually sort of creating, and not just creating this patch, but then sort of providing the the trail of crumbs to help me figure out the parts that I got stuck on. I've really enjoyed learning this, starting to see how things can come together this way, and there are still obviously holes in my understanding, but they're shrinking. They're getting smaller, and I hope this was able to shrink the size of the holes for some of the viewers as well. If anyone has any comments or questions before I sign off for the day, feel free to post them in the chat log. This is fun for sure. I'm glad it was fun and not painful for me to sort of hack my way through your code. Um, and thanks for joining. I really appreciate it. All right, so I think that's it for comments. So we'll do a much more basic introduction to jitter in the allotted class time tomorrow. You won't get into anything this complex. So if this just lost you from the get-go, um, then perhaps tomorrow we can find a good starting point for this type of conversation. And until then, uh, happy patching, everybody. And I'll see you soon.